Thank you very much, Raman. I would like to thank you, organizer, that give me opportunity to present my research at your seminar. So today I would like to talk about the 1D nanostructured materials for the energy conversion. Let me introduce myself. So I finished my PhD at the Faculty of Mathematics and Physics at the Charles University in Prague in 2005. So then I moved to Japan in 2005 and I worked at NIMS for about 5 years as a postdoctoral researcher and then GSPS fellow on the few projects, which is shown here. And then in 2010, I moved to the University of Tokyo on where I'm working until present time. So I'm running many projects. But right now, what I'm doing, so this is very special project. So this is solar hydrogen production. So actually now I'm working in the one of the biggest artificial center. So this is the first center in Japan. So it's include around 100 people from the not only universities and institutions, but also from the private companies. Okay, so let me start my presentation. And now I would like to explain you what is the main motivation for this work and why I'm doing this research. Okay, I will turn the videos because I need to see slides. Okay, sorry. Okay, as you know, there is 6 waves of innovations, which the first started from the year 1785. So this is the first innovations. This is industrial revolution. Okay, so which is followed on the second wave. This is steam engine developing and realization, and then there is the third wave electricity development. And then this is the first wave, this is automobile, aviation, and the oil industry. So, and there is next one, fifth wave, information technology, and where we are now. So this is the new waves. So there is the big plan for the connection of more than 50 billion connected devices through the developed 5G system. So there is a plan, the whole system design, new energy, nanotechnology, renewable fuel for the transportation and vehicles. However, there is requirement. So we need renewable green energy resources. So such as solar hydrogen production for autonomous microfuel cell, lithium-ion batteries, solar cell, and etc. Okay, and today I will mainly talk about the energy conversion nanostructured materials. So I will show you design, fabrication, and the application of such materials. So I will mainly talk about the one-dimensional oxide materials, which can be integrated with the photocatalyst, for example, together with the photovoltaics and photoelectrochemical cell for the hydrogen production. Then I will also show another material which are based on the oxynitrides. And then I will show you some practical application of the developed one-dimensional nanostructured material, for example, as a self-rechargeable microfuel cell or lithium-ion batteries on which we have worked together with Roman when he was in Japan. Okay, so let me now explain why nanostructure. Okay, the nanostructured materials offer various advantages as they provide more flexible space for ease the construction as they nanosize expand the limit and results in confinement effect, enhance mechanical stability and large surface area, and make them suitable for the photocatalytic activities or energy storage devices. As you can see here, so this is the simple thin film. So the main disadvantage of the thin film, because it has a small surface area and of course there is poor charge separation and low mechanical stability. On the other hand, if we look on the nanoparticulate based film, so we have large surface area. However, there is moderate charge separation and mechanical stability. In the case of the one-dimensional nanostructure material, so we have together enhanced surface area, excellent charge separation, and enhanced mechanical stability. So now I would like to explain you the basics about the photoelectrochemical process. Okay, what we can see here, so this is photoelectrochemical cell, which consists of, it can be like a glass square, on where is the electrolyte. So here is immersed photoactive semiconductor materials, and here we have the counter electrode, which is usually platinum, and it's connected in series with the platinum, I mean the semiconductor with the platinum electrode. So in the case when the light is illuminated, actually we can produce the holes on the surface of the semiconductor, and then holes are oxidized water, and we can produce the oxygen and the free electrons. So then the free electrons are extracted by external electrical circuit and comes to the counter electrode, on where meet the protons, and then we can produce catalytically hydrogen. So this is very simple, but very popular and green energy resource. Okay, now let me start from the first one. So this is one-dimensional oxide materials, which are tungsten oxide and bismuth vanadate. Okay, so let me explain the motivation to use nanostructured material for the solar hydrogen production. So here, he is developed recently by me, titanium dioxide brush type nanostructure. So this is the same image of the fabricated material. So what we can see here, so this is titanium core, and here is the titanium dioxide shell. So of course, this material has a large surface area, and the working principle, I mean the photocatalytic working principle is shown here. So when the light is irradiated, actually we can produce the pairs, which are hole and the electrons. So hole are extracted to oxidize water, and the electron come to the core, very conductive core, and can reach the conductive substrate, and then can be realized on the hydrogen production on the platinum counter electrode. However, there is a big problem of the titanium dioxide material due to very small band gap, which is, wide band gap, which is 3.2 electron volts. And if you look on the quantum efficiency of such materials, as you can see here, we can utilize very, very small fraction. I mean, we can absorb very, very small fraction of the from the solar light. I mean photons from the solar light, because here it only exists around 3% of the photons. So, however, if we look now on the bismuth vanadate material, so here the absorption age is quite wide, which is around 550 nanometer, and we can see here that we can utilize about 50% of the photons from the solar spectrum. And the theoretical solar to hydrogen conversion efficiency, which can be theoretically realized, is 9.5%. So as you can see here, it's just about 0.1%, but here is 9.5%. So it's very excellent material. So I was very motivated for this material when I read the paper, which was published in the Nano Letters in 2011. So at that time, Grimes realized experimentally solar to hydrogen conversion efficiency 0.6% on the random structure. So what we can see here from this SEM image, so here we have the tungsten oxide nanorod, which are covered by bismuth vanadate material. So, however, my idea was different. So how about the well-controlled structure by bottom-up fabrication, and then cover this one-dimensional material by the bismuth vanadate. If we look to the band diagram of both materials, you can see here the conduction band of bismuth vanadate is located a little bit higher than conduction band of tungsten oxide. That means that generated electron can pass through this material very easily and can reach conductive substrate. So what we expected for such photoactive material, so we expected efficient light harvesting and the charge transfer. In order to do that, first I considering about the photoanode design. So I considering deeply about the material properties. So what we know about bismuth vanillate? It's very good absorber, however, bad conductor. Bad conductor, it means that the diffusion length of hole had a very, very short distance. On the other hand, tungsten oxide is bad absorber, but very good conductor. So if we combine this material together, we can create excellent photoanode material. Okay, so this is the model. And what we can see here, so here is the H, it means the thickness of the bismuth vanillate material. D, this is distances between center of the nanorod. L is the length of the nanorod, and R is radius of the nanorod. From the theoretical approach, we know that, for example, if the thickness of material increase, so absorption is also increasing. And once we reach the certain thickness of the material, the absorption will saturate it. So we don't need to deposit it more material because we already reach absorption. However, if the material exceeds the appropriate thickness, so then we will have IPC increases due to the resistive losses in the long conductive tungsten oxide nanorod. The similar scenario is also for the bismuth vanillate. So thus, if we look here on this relation, so only there is exists only a quite small window for the optimization of that material on where it will absorb enough light, had a very good charge separation ability, and enhance surface area. So in order to fabricate such materials, what we need to do, we have to precisely control nanorod diameter, density, and length, as well as bismuth vanillate shell thickness, and also material crystallinity. Okay, so let's play with atoms. So now I will briefly explain you what is the glancing angle deposition technique. So here is shown the principle. So usually GLAD setup consists of the magnetron source or another source which can evaporate the material. It can be like an electron beam gun or maybe simple evaporator. And the most important part, this is the substrate holder, because we should control precisely two rotations. So as shown here, this is gamma rotation. It's control the rotation in this direction. And the alpha rotation, it gives you the incident angle, deposition angle, which is usually in between 65, 85 degrees. Okay, now about the principle of the nanorod growing. So if you're considering that the atom is already deposited on the substrate, so these atoms create shadow to the other incident atoms. And due to the limited atom diffusion, we can eventually produce the slanted nanorods. However, if we rotate substrate with respect to the deposition rate of the materials, so the nanorod will grow vertical. Here is shown the main parameter for the GLAD experiment. So this is the low pressure, which is usually in the range of from 0.1 Pascal up to 0.5 Pascal, and long through. So this means this is distance between source to the center of the rotatable substrate. And this both parameter is called LPLT, which help us reduce the scattering component of flux from the magnetron. And of course, if we want to operate at the lower pressure, so we need a very strong magnetic field of the magnetron. Okay, so for that purpose, I developed a magnetron. And here is shown my custom design. So this is the calculated magnetic flux. So, and then the company built this device. So, and if you compare the price, so for example, this is commercial magnetron price, which is cost around 1 million yen. So it's around $10,000 or something. However, the price for this magnetron is around 7 times lower. Okay, but this is not important. Okay, and this is the picture of the GLAD system, which I also designed. So what we can see here, it consists of the two chambers. So the main chamber and the introduction chamber. And here is the 4-step motors for controlling of the substrate motion. And this is picture inside of the equipment. So here we have the specially designed motion mechanism. So actually we can rotate in the both direction substrates, and as well as we can change the position of the substrate as well as the distance. So this is the magnetrons, which is located here, 4 pieces. And the gas mixture system connected to each magnetron. Actually, we can work with the 3 gases, which is usually argon, nitrogen, and oxygen. And this is just a short video to show you how I'm flexible with this system design. So this system design allows sputtering of various kind of metal oxide and nitrides. So also this GLAD system working not only for the nanostructure fabrication, but also for the thin film. And then also we can do the co-sputtering process. Okay, so I need to maybe by pointer I could not show you the video. Okay, so this is just to show you. So this is the source, and here is the plasma, and this is the substrate holder during the rotation process. Okay. Okay, and the next slide, this is again tungsten oxide core bismuth vanadate heterojunction nanorod for the solar hydrogen production. So we started to fabricate this photoactive material at first by using GLAD system to fabricate tungsten oxide nanorods, which following the electrochemical deposition of the bismuth vanadate. So, and here is shown the optimized samples. So what we can see here very nicely, vertical tungsten oxide nanorod, which is here, and a very thin layer of the bismuth vanadate. And also this bismuth vanadate was deposited like a nanoparticles. Okay, and about the solar hydrogen production. So this is the gas the result from the gas chromatography on the detection of the hydrogen and oxygen during the evolving. So if we compare titanium dioxide, the rate of evolved gases. So on this material, we realized about 60 times enhancement for the production of the hydrogen. So it's really big number. So in the next step, what we do, so in collaboration with AST, so we prepare photovoltaic photoelectrochemical tandem design, which is shown. And this is design, and now you can see the fabricated device. So what we can see here, so this is the photovoltaic cell, and here is the photoanode. Okay, and this is the IV characteristic of that device under the one sun and the room temperature. So the blue line corresponds to the IV characteristic of the photoanode, and this line corresponds to the IV characteristic of the solar cell. The point on where this two lines is cross, so actually this is ST, solar to hydrogen conversion efficiency number. So as you can see here, we realized 8.5%, 8.1% of STH, which is still world record for that material. Actually, this work was published in 2015, so it's quite a long time. Okay, and now let me move to the another material. I will explain you why we change material. So in order to commercialize solar hydrogen production, so there is need, efficiency should be more than 10%, but efficiency of the material is given by the band gap material, the band gap of the material. So the most ideally, the band gap should be in the range of 1.7 to 2 electron volt. And also about the material durability, so it must be stable in the aqueous solution during the solar irradiation and the gas production. Okay, so I was motivated with my previous work, and I'm considering about another material, which is tantal 3 and 5. If you look here, so the solar to hydrogen conversion efficiency, theoretical, of this material is around almost 16%. So this is really ideal material. So, and from our previous work, what we know about this material, which we a little bit work on that, we developed the nanorod. However, this nanorod was prepared by the electrochemical processes. So, and here is the two limited factor. At first, during that process, thick interlayer is appear, and this subnitride layer, so it's not well conductive. So that means that we have losses in the electron transport. And secondly, the nanorod are partially stuck. So this is also bad because we have losses in the total surface area. So for that reason, the idea is well-oriented nanorod, which can be grown by the glancing angle deposition technique. So advantages of that technique and also prepared nanorod that we don't have no interlayer, and also if we will develop the good parameters, so we don't have any stacking of the nanorod. So this is just schematically shown how we deposited nanorod with the main parameter. And this is just a SEM image as deposited material. So this is still amorphous because we are working in the argon and the oxygen plasma. So then this sample should be nitridized. So, and here is shown schematically nitridization process. So what we can see here, so this is quartz tube and the heater. And from this direction are connected to nitrogen or ammonia. So nitrogen is needed to take off the air. So we have to push the tube within 30 minutes. And then we switch to to ammonia and started to increase the temperature up to 980 degrees, and then followed the nitridization in ammonia for about 2 hours, and then normally cooling. And then the co-catalyst loading on the tantal 3 and 5 nanorod based photoanode. And this is the picture of the fabricated photoactive material. So as you can see, this material has a quite very nice red color because the band gap is about 2.1 electron volt. So of course, there is many parameters to control the nanorod quality because the photoelectrochemical performance is very deeply depends on the diameter of the nanorod as well as crystallinities. I will explain you why. So what we can see here in the red square and the blue square. So this is the optimized material and this is non-optimized material. If we compare optimized and non-optimized material from the XRD analysis, there is almost no differences, very, very similar. However, if we look deeply from the TM analysis, so especially from the from the dark field, and also from that analysis, we can say that this material is polycrystalline. Actually, both materials are polycrystalline. And from the dark field, we can see the size domain. So if we compare the optimized and non-optimized material, so the size domain is about 3 times higher in comparison to the non-optimized material. So thus we expect that we will have the higher conductivity in optimized nanorod and better electron transport. This is absolutely similar case like in the CAGS solar cell. So if the size domain is big, solar cell working well. If it's small, so of course efficiency is lower. So this is due to the conductivity of the material. Okay. And then we started to evaluate performance of this material, optimized and non-optimized material. As you can see, non-optimized photoanode show at the 1.2 volt versus RHA about 10 milliampere of the photocurrent. However, the fill factor is very, very bad. But in the other hand, optimized photoanode show excellent fill factor. And also the saturated photocurrent, which was saturated around 10 milliamp, and the applied voltage of about 1 volt. So it's really excellent. Okay. And if we now look on the quantum efficiency for the both material, we can see that optimized photoanode show us almost twice enhancement in this region. Okay, and then we calculated the fill factor. So this is actually the first time demonstration of the calculation fill factor for the photoanode. So, and we realized 42%. And this is due to the big size domain. Actually, large grain domains in tantalum 5 nanorods improve conductivity and provide enhanced light harvesting, which owing to the efficient generation and extraction of the charge carriers that leads to the saturated photocurrent of about 10 milliamp. Very nice. Okay, and then we evaluated the gas evolution rate in the same cell, but just connected the gas chromatograph here. And as you can see here, so this is the video of the process of the generation. So what we can see here, so this is photoanode material. So this tiny bubble, so this is the oxygen. This is our photoanode, and this is the platinum counter electrode, and this is the reference electrode. So here, maybe you can see, or I don't know, if not. So there is also tiny bubbling. So this is the hydrogen generation. So in conclusion to that, so stoichiometric fuel generation rate was detected with about 95% of Faradaic efficiency and relatively stable photocurrent of about 80% of retention. So it's quite stable. Okay, now if we compare the tungsten oxide, bismuth vanadate core shell structure with the just simple tantalum 5 nanorods, so we again had improvement on 1.5. So yeah, so this material is really very, very promising. Okay, and now let me show another result, which is based on the oxynitride material. So this is, I will show you quite a new result, which was published just at the end of last year. Okay, so this material is called barium tantal oxynitride because its band gap is much lower. It's 1.9 electron volt. So thus it can generate around 18 milliamp per centimeter square of the photocurrent, and the solar to hydrogen conversion efficiency theoretical can be 21%. So it's about 6% higher in comparison to the tantalum 5. Okay, by the combination of the oxide and nitrides, so we can actually develop another efficient photoanode material. So now let's look what we know about the barium tantal oxynitride material. So there is advantage and disadvantage. So in the case of advantages, so the material has a direct band gap, which is 1.9 electron volt. And this material is excellent absorber. However, this material has a poor conductor and short carrier diffusion length. It's similar to the bismuth vanadate.
Hello?
Yes.
Yuriy, we lost you for a while.
Oh, really?
Yeah.
Your internet connection is unstable? Can you hear me now?
Yes.
Okay. Okay, so for that purpose, so we again prepare the conceptual design. And as you can see here, the location of the conduction band for the barium tantal oxynitride is lower, so that means that higher. That means the electron can be very easily passed. Okay, so and then we asked the theoretical guy, so in which we collaborated with AST, so who is Dr. Nando, and he simulated that model and show the possibility that we can realize such kind of nanostructure because lifetime of the carrier is about 1 nanosecond, and he predicted high current density at this potential. So actually, this is the potential which minimum potential which require for the water splitting. Okay, and as well as low onset potential due to the less charge carrier recombination, owing to conduction band offset near the nanorod surface. Okay. So then again, we started the deposition of the tantalum nanorods, this time just metal. I will explain you why. And then we are loading the barium-rich precursor on tantalum nanorod by using the deep coating techniques. Then follow the oxidization of barium precursor in order to take off the organics from the barium-rich precursor. And then final stage is the nitridization to make the core shell nanostructure. Okay, and now I will show you morphology and structural analysis of the fabricated core shell one-dimensional tantal 3 and 5 nanorod bitantal oxynitride photoanode. So the blue from the XRD pattern, so this is the blue for the tantal 3 and 5 nanorod, is very well fitted with the original material from the database. And here is shown just two ratio of the barium-rich precursor, which was used for the creation of the core shell nanostructure. So, for example, if the ratio barium to tantal is 1 to 1, so we could not detect baritantal oxynitride peak, which is shown here. However, if we a little bit increase the ratio, which is 1.25 to 1, so then we detected very tiny peak. So this tiny peak is due to because, as I told you, this is electronically seen material, but optically sepia. So it's not enough material to get a good peak from the XRD. So for that reason, it's again, the TEM analysis is required, because in the high resolution TEM, we can directly see the planes from the materials. And by measuring the distances in the plane, so it can give us information about if it's really baritantal oxynitride material or not, and also from the diffraction pattern. So the formation of the baritantal oxynitride on tantalum nanorod were confirmed by high resolution TEM. And then we use STM-EDS mapping to show the uniform distribution of the barium element across the nanorod. Okay, and then this is again IV characteristic of the both materials. So this is blue one, tantalum nanorod, tantal 5 nanorod, and the red one is core shell nanostructure. So you can see here we have good enhancement. But what is very interesting, this is band gap shift due to the baritantal oxynitride. So this is exactly at the 2.1, at the 1.9 electron volt. So this is the third confirmation that we realized this structure. And about the rate of evolved gases, so its results shown here. So we detected stoichiometric field generation rate, 90% of Faradaic efficiency, and very, very stable photocurrent of about 4.3 milliamp. So because the barium tantal oxynitride, this material is much stable than tantal 3 and 5. However, the further optimization of the length of the nanorod diameter, as well as thickness of the baritantal oxynitride is required. So, but this result is just confirm the proof of principle of the proposed one-dimensional nanostructured material. Okay, now let me shift for the to show you the real practical application of the developed material in the case of rechargeable micro fuel cell device. So this is the totally integrated microfluidic device for the solar hydrogen generation and the fuel cell. And here is shown the device design. So this device consists of two parts. So the fuel supplier and the fuel cell. So what we have inside, so this is integrated tungsten oxide bismuth vanadate material to the microchannel one. Here is the platinum counter electrode here integrated. And these two microchannel are connected by extended nanochannel. So this is for the proton transport. And here we have the shell of microchannel, which are modified by the fluoropolymer. So this is why we need. This is for the gas separation because water could not come here due to the huge Laplace pressure. Okay, if you see here dimensional of this introduction microchannel and hydrophobic microchannel, so it's really tiny. So this is in the micrometer range. And in the case of the fuel cell, what we have here, so this is integrated platinum counter electrode, and the anode is platinum palladium composite materials. So another very important part, this device should be connected physically, yeah, but electrically should be disconnected. I will explain you how we realize this one by using the very tiny nano channel, just one. And now I will explain you the working principle of that device. So when the solar light is applied and irradiated the photoactive material, so we can eventually split the water for the electrons, oxygen, and the free protons. So the protons are extracted by the extended nanochannels, and the electron comes to the electrical circuit, reach the platinum electrode, and catalytically produce the hydrogen. Next step is the separation into the hydrophobic channel, and then gas diffusion to the fuel cell part. So in the fuel cell, so the electricity are generated. Yeah, it's shown here. And then the final product is water. So of course, here we have overpressure because if you generate a lot of electricity from the hydrogen and oxygen, so then the water is produced. So then we need to return water to this device because here is water splitting. Okay, so for this purpose, the nanochannel was designed, and we measure the resistance of this nanochannel, and it's very, very big. So it's around 1,200 megawatt. That means that these both devices are electrically disconnected. However, physically it's connected. Okay, and the water comes here. So this is the photo of the fabricated, this is actually design, and this is the fabricated device. So this device was realized on the quartz plates. So, and what we can see here, so this is integrated photoanode material, and SEM image is shown here. So it was recorded by SEM directly from this device. And integrated platinum cathode and the platinum anode. And this is a SEM image of the extended nanochannel. I mean the arrays of the extended nanochannels, which are located here and here. And this nanochannel that used for the connection of these both devices located here. Okay, and now the device performance. So this is the photo of the real device. These holes, yeah, you know, this is the point from which we extract the gases. And all, okay, so from the hydrophobic channel, so we extracted the gases. But from this one, so we introduce the water to this device. So actually, the working area of this device is only very, very small, only here and here. So actually, why this device is big is because we need to evaluate this device. Okay, but actually, this device can be realized in the much smaller size as is shown here. Okay, now what I will show is the video of the fuel generation, which was recorded through the microscope, of course. So this is just normally video recorded from the normal optical microscope. So what we can see here, so this is hydrophobic microchannel 1 and second 2. And here's the integrated photoanode and the counter platinum electrode. And this is the extended nanochannel, the arrays of extended nanochannels. Okay, now we will generate oxygen and the hydrogen, and you will see it. Okay, and then separation process. Okay, and the time when we irradiate it, so you can see. So the water started to split and it's bubbling and gases come to the hydrophobic microchannel. So oxygen comes here and hydrogen comes here. So this is solar light assisted fuel generation and automatic separation. Then fuel diffusion to the fuel cell and electricity production, and the final output product is water. Okay, so to confirm the working principle, of course, not only enough to record just video, so we need to also record the signal from the both devices. So what we can see here, so this is photocurrent time characteristic of the fuel generator, and this is power time characteristic of the fuel cell. Okay, so in the time when we started to radiate the photoanode, I mean the fuel generator, so the photocurrent was recorded, in which, so actually this is process of the water splitting, so this is oxygen and hydrogen production. Okay, so then we need about 20 minutes to generate enough gas which will reach the fuel cell, and then, as you can see here, the power started to increase. So actually this is the activation, and then this is the activation of the fuel cell. It's required about 10 minutes, I mean, for the stabilization. And then within the continuously irradiation of the device, so the fuel cell produced the electricity, which is around 6 microwatt per centimeter square. And then at that time, it's around 90 minutes, we stop the irradiation. However, as you can see here, the fuel cell continued work for additional 20 minutes, about 20 minutes. So this is because of the fuel is still remain in these microchannels. And then the power started to decrease because there's no fuel. Okay, and this is the final results. So this is based on the lithium-ion batteries, which has been done at collaboration with Dr. Roman Bakirevich. So this is very simple principle of the lithium-ion battery. So usually the lithium-ion battery is consist of the anode and cathode and membrane electrolyte. So during the charging, lithium ions are released by the cathode and intercalate to the anode. In the case of the discharging, it's the opposite. Lithium ions move from anode to cathode and power is generated. However, here is requirement on the anode material. So the anode material should have large capability of the lithium absorption, high efficiency of the charge and discharge, excellent cyclability, fast reaction rate, low cost, and of course it should be non-toxic material. So one of the good candidates is again tungsten oxide, because the theoretical capacity is around 700 milliamp per gram, with the quite large volumetric capacity, which is around 5,270 milliamp hour per cubic centimeter. However, there is a problem with conventional tungsten oxide based anodes. For example, in the nanoparticulate system or random nanorods or nanoflowers or thin film etc., because there is low cycling stability and pure rate performance. So for that reason, we fabricated with Dr. Bakirevich the tungsten oxide nanorods directly on the current collector. And this is the SEM image of the collector. And then we utilize TM techniques to confirm crystallinity of tungsten oxide material as well as XRD also confirm monoclinic phase of that material. So, and then the coin cell were were fabricated, and this is just show you from what part this coin cell consists. So then we recorded CV, and as you can see here from the first cycle, there is a say formation layer, but after the during the second cycle, third, fourth cycle, this say was already formed, and as you can see here, it's quite stable material. So what is the very interesting result here? The cyclic performance at this 80 milliamp per gram. So it's relatively a stable material during the cycle number. However, there is a small degradation rate. But this is interesting, okay? If we look on this graph, we can see that if we change the C rate to the smaller one, so this material are recovered. So what does it mean? It means that if we choose appropriate C rate for the charging and discharging, so actually we can save the lifetime of this material. So this means that, for example, it's depending how fast we want to charge this battery, 5 minutes or 10 minutes. So actually, you see, this is really a unique material. And if you compare the other material with already published one, so the other material show very nice specific capacity and also lifetime. Okay, and this is the last result, which Dr. Roman Bakarevich recorded. So this is the in situ time analysis, how our nanorod absorb lithium ion and how it expand. So actually, why nanorod is good, because each material which absorb lithium ions is expand. So, however, the nanorod is good because it's well separated. Actually, if it's expand, so there is enough space, right, in all directions. Okay, so and thus it can save us lifetime of the anode. Okay, and here is the video. So this is nanorod and this is lithium material. So when it's in contact, applied some voltage. What we can see here, this is expansion of the nanorod. Okay, it's very nice to see. And in the case when the lithium is released from the tungsten oxide, so this nanorod, it's returned to the previous stage. So actually, this is some kind of like nano breathing anode. Okay, so this is the last slide. So this is the conclusion. So we developed tungsten oxide nanorod bismuth vanadate core shell nanostructured photoanode with a stable photocurrent of around 6.7 milliamp and realize about 8.1% of solar to hydrogen conversion efficiency. So we designed and fabricated an efficient tantalum SIN5 nanorod based photoanode for solar hydrogen production. And also we realized a solar light driven fully integrated microfluidic device that can serve as autonomous fuel cell based power source for microsensor or lab on a chip application. And finally, we realized binder-free anode that based on the one-dimensional tungsten oxide nanorod for the fast charging of lithium-ion batteries. So thank you very much for your kind attention.
Thank you very much for a very interesting talk. It was especially interesting to see the limitation of traditional technique like XRD and see how transmission electron microscopy help you to give very beautiful conclusions. And now our presentation is open for discussion. We, of course, short in time, but still have time for 1 or 2 short questions. If anyone want to ask, please unmute yourself and ask questions. Maybe nobody. Okay, so then I will ask you about, you mentioned in the very beginning of your presentation about titanium O2 brush type nanorods. And did you try to realize the same brush type WO3 and bismuth vanadium O4 structure? It will have any advantages or not?
Yeah, Roman. Actually, this is Roman, what we did in the next hour work. So this is the similar case. So this actually bismuth vanadate is a shell structure, okay, and the core is tungsten oxide. That's shown here. This is design, okay. However, this technique is completely different. So this is anodization technique. Yeah, but here is the combination of two different materials. So for that reason, we need electrochemical deposition.
Okay. Does anyone want to ask something?
Yeah, I have a question here.
Yeah, please.
Right. So I'm working with 2D materials for lithium-ion batteries, and I was wondering, is it possible to make nanorods out of any 2D material? Is that like a specific a quality you have to look for before making them in nanorods, or can you make nanorods out of maxines, phosphorines? Is that possible?
What kind of material? I'm sorry, I could not recognize. Could you please repeat what kind of material?
For example, like maxines or phosphorines. Is it possible to make nanorods out of these materials?
Okay, if it's a solid material, and if it's possible, if it's solid material, and if it's possible deposited, in this case, yes.
Okay, yeah.
Just by sputtering.
Right, yeah, because I haven't tried it yet.
If it exists sputtering target material, yes. In this case, yes, I can.
Well, all right, thank you.
Okay, anyone else? Maybe not. So let's thank our speaker and see you in 2 weeks on our next At Home with Nano seminar with Dr. Daniel Mararo from Shizuoka University. So see you in 2 weeks. Thank you very much for everybody. Goodbye.
Thank you.
Thank you very much.
Thanks.
Thank you.